All right, so let's start problem solving of chapter 4. All right, so let's start with this one, the first one. Okay, the first one is the easy one. So what it said. So it says that suppose that the net external force exerted on a lawnmower is 51 Newton parallel to the ground. The mass of the mower is 24 kilogram. What is the acceleration? Okay, so what we need here. Okay, so to solve we need the Newton's law. Okay, so the Newton's second law tells us that F equal to ma. Basically we need the x direction, right? Fx max. So because here it already tells you that the net force is equal to 51 Newton and the lawnmower's mass is 24 kilogram. So we can plug these two values. So 51 Newton equal to m m is 24 kilogram. So 24 kilogram times ax. So ax is 51 Newton divided by 24 kilogram, and it is 2.1 meter per second square. The unit of acceleration is meter per second square. So this is the easiest one. All right, let's move on. So let's see what it asks us to calculate. So in the second problem, it says that what average net force is required to bring a 1500 kilogram car to rest from a speed of 100 kilometer per hour within a distance of 55 meter. Okay, so the initial velocity is given, that is 100 kilometer. So v0 is 100 kilometer per hour. Okay, so see that this is not in meter per second, not in standard international unit. So you have to convert it into standard international unit. So 100 times 1000 or 10 to the power 3 for kilometer to meter, and then 3600 for hour to second. So what we have here is 27.8 meter per second. Okay, all right, so the initial velocity is this, final velocity is 0. X0 is 0, x equal to 55 meter. Okay, so it says that what force we need to stop this car while it was running at 27.8 meter per second. Okay, so when a car is moving at 27.8 meter per second, if you want to stop it, you have to hit the brake, right? So braking means you are applying force. Okay, so that force we have to calculate. Okay, now we know that F net, or sum of the F, is equal to ma. So here all the things are x-axis, so you can either write this, or if you don't write this, it should be fine, because the only forces or only component we have is x component. Okay, so this is the equation. Now to calculate F, we need m and a, right? The mass and acceleration. Mass is 1500 kilogram. So if I want to calculate the force, we basically need to calculate first the acceleration, right? So we have to first calculate acceleration. So how to calculate acceleration? Now To calculate acceleration, we have to recall some kinematic equation that we learned in chapter 2. Okay, so we are given initial velocity, final velocity, initial position, final position. So this is basically x is 0 and this is x. Okay, so with this, what equation is useful to calculate the acceleration? Okay, so I think this is useful equation, v squared, the last kinematic equation. Okay, so this is the kinematic equation, and this is useful to solve a here. So you can call it ax. Okay, now here this is 0, right? The final velocity is 0. This is v squared, and then 2ax, x, and x0 equal to 0. So what we get is v0 square plus 2ax x. So 2ax x equal to minus v0 square. So ax is equal to minus v0 square 2x. Okay. Now here v0 is this. Okay, v0 is this, and x is 55. Okay, so if you plug these two values here, you should get, okay, let me plug. So minus v0 is 27.8 meter per second square, and then 255 meter. So that gives us minus 7 meter per second square. So the acceleration what we get is minus 7 meter per second square. Okay, it makes sense getting a negative sign because we are deaccelerating here, right? We are decreasing the velocity. So initial velocity was 27.8 and final velocity is 0. So we are deaccelerating our car. That means we should have a negative sign in the acceleration. Okay, so this is the acceleration. So what is the force? Force is Fx equal to m is 1500 kilogram and a is minus 7 meter per second square. So when you multiply these two, you should get something like this. Okay, so 10,500 Newton, and a negative sign tells us that the direction of the force is this direction, opposite to the direction of the velocity. All right. All right, so let's move on. The next problem is, so a friend has given you a special gift, a box of mass 10 kilogram with a mystery surprise inside. The box is resting on a smooth, frictionless horizontal surface on a table. Determine the weight of the box and the normal force exerted on it by the table. So for the first problem, okay, so here we have the table, frictionless table. Here we have the box. Okay, so let's draw the free body diagram. Okay, so free body diagram will be something like this. This is the gravitational force and this is the normal force. So this is the normal force. Okay, and because it is staying okay, so because the object is staying at rest, there is no other things to to draw here. Okay. So the gravitational force, it asks us to calculate the gravitational force. So gravitational force will be W equal to mg. M is 10 kg, and the gravitational force is 9.80 meter per second square. So it will be 98 Newton. Okay. Now how to calculate the normal force here? Okay, so this is our free body diagram, and you see that there is no acceleration here, neither along the x or y axis. Okay, so if I want to write down the Newton's second law, so Newton's second law tells us that Fy equal to may, right? Because all the forces are along the y direction, the only equation we need is the y component. So this is the equation. Now we know that there is no acceleration, so the acceleration is equal to 0. That means right hand side is also equal to 0. Okay, so now on the left hand side we have to explicitly write the components. Okay, so we have normal force in the positive y direction, and the gravity in the negative y direction. Okay, so this is the equation. Now if I solve this equation for normal force, I get N equal to mg, and we already calculated mg equal to 98 Newton. So the normal force here will be 98 Newton. Okay, all right, so that was for A. Now B said that now your friend pushes down the box with a force of 40 Newton. So now there is another force, that is push force. Okay, let me call it Fp. Okay, now let me erase this. Okay, so here we have Fp. Again, I mean, it says that now your friend pushes down the box with a force of 40 Newton. Again, determine the normal force exerted on the box by the table. Okay, so when someone push this box to the, push this box by 40 Newton force, nothing will happen. Actually, it will not move in any way. Okay, so but then if someone apply another force, okay, P, what is the normal force? Okay, so in the first problem you see that the normal force was equal to, for the first problem it was equal to mg, and that was 98 Newton, right? We already see it. Now in number B we can follow the same equation, same rule, okay, same technique, and see that what is the normal force now. Again the right hand side equal to 0. Why? Because there is no acceleration, there is no motion. Okay, so the right hand side equal to 0, but the left hand side now is little bit different. Okay, so the normal force along the positive y, Fp is along the negative y, mg is along the negative y. So Fp, and for mg we have negative sign because Fp and mg are downward. On the other hand, n is upward. So for upward we have positive sign, for downward we have negative sign. So n equal to Fp plus mg. Okay, so Fp is 40 Newton, right, and mg is 90 Newton, right? That that we already calculated in the first problem, number A. Okay, so in this case you see that the normal force is 138 Newton, which is different than the last problem. So you see that normal force is not always equal to the gravitational force. For some problem it is equal to the gravitational force, but it is not always the case. Okay, all right, then the last one, Let me erase it. So here N equal to 138 Newton. Okay. Number C. So now it says that if your friend pulls upward on the box with a force 40 Newton, what now is the normal force exerted on the box by the table? Okay. So this time it's not downward. It says that now your friend is applying, pulling this up box upward. So now the force is in this direction. There is another force, Fp. Let me still call Fp because it's pulling. Someone is pulling by 40 Newton, but it is now upward. Okay. So what is now the net force? Okay. Now, okay. So what is the net force? So again, when Fp is only 40 Newton, okay, so to pull it, so here we already know this is 98 Newton, right? The weight of this box is 98 Newton. Now, if you want to pull it, okay, upward, so you need at least 99, at least greater than 98 Newton force. If you want to hang it, okay, if you want to hang from, if you want to pull it upward, okay, so you need at least 98 Newton of force, okay, so that it will no longer be on the table, it will be hanging on air. Okay, but here it says that it is only 40 Newton. Okay, so because the upward pulling force is only 48 Newton, it will be still on the table. Okay, sorry, 40 Newton, not 48. Okay, so because your friend is pulling it only by 40 Newton force, the box will still be on the table. Okay, so that means there will be no motion of this box. Okay, so again we can use the same technique, Fy equal to MAY, and there will be no motion, so the right hand side or the acceleration is equal to 0, so we can write this, but the left hand side is now something like this, plus N plus Fp because both are upward, and minus mg because mg is downward, that is equal to 0. So N will be mg minus Fp. Okay, and we already know that mg is equal to 98 Newton and Fp equal to 40 Newton. Okay, and that means it is equal to 58 Newton. So the normal force in this case is 58 Newton. So you see that depending on what other forces acting on the object, normal force could be different. But important thing here to remember, if there is only gravitational force and the normal force are there, then it is equal to the normal force is equal to the gravitational force. Okay, all right. Okay, so it's basically number 4 is basically the continuation of the last problem. Okay, so in the last problem your friend pull it up by 40 Newton. So 40 Newton is not enough is not enough to move it up. Okay, so as you know that if the box's weight is 98 Newton, you need at least 90, at least higher force than 98 Newton. Okay, so if it is below 90 Newton, you cannot move it. Okay, it will be still on the table. But if the force is more than 90 Newton, it will be no longer on the table, it will be moving upward. Okay, so in this problem it says that what happened when a person pulls upward on the box in the last problem with a force equal to or greater than the box's weight. Okay, for example, let P equal to 100 Newton. So what happen if you or someone pull it at 100 Newton force? Okay, so because the box's weight is 98 Newton, so 100 Newton is higher than 98 Newton, so it will be moving upward. Okay, so let's see. Okay, so the answer is, yeah, it will be moving upward. That means it is that means the net force is not equal to 0. Right now you see that the downward force is, okay, so downward force is 98 Newton, the gravitational force. Upward force is 100 Newton, and now the box is no longer on the table. Okay, so the table is here. Okay, so when the upward force is higher than the gravitational force, it will be moving upward, right? So when it is not on some surface, then the normal force is equal to 0. Okay, so without any calculation, you can tell that normal force is equal to 0 because it is no longer on any surface. It is no longer on the table. Okay, now I want to, because here the net force is not equal to 0, that means the object is moving upward with some acceleration. So I want to know what is the acceleration here also. Okay, so let's try to calculate what is the acceleration. Okay, so again the technique is similar. As all the forces are along the y direction, the only thing we need is this equation, the y component. Okay, and because Fp is higher than 98 Newton, if there is some acceleration, it will be in this direction, upward, right? So Fp upward, mg downward, plus ma. So this plus sign tells us that acceleration is upward. Okay, so this plus sign is not that important in this problem, but sometime when the acceleration is downward, then we have to explicitly mention the negative sign here. Okay, so that's why it's better to use the positive and negative sign explicitly. Okay, so here it doesn't matter, but in some problem we will see that it is matter. Okay, so when it is matter, okay, if you don't use a negative sign, explicit negative sign, you will get a wrong answer. Okay, so make sure you understand this. Okay, all right, so I want to know what is the acceleration. Okay, so this is 100 Newton, 100 minus 98 ma. So this is, so left hand side is 2 Newton ma. So a equal to 2 Newton divided by m is 10 kilogram. So 2 Newton, 2 divided by 10 is 0.2 meter per second square. So this box will be moving upward with 0.2 meter per second square acceleration. Okay. All right. Next problem. So it says that a 65 kilogram woman descends in an elevator that briefly accelerates at 0.20 times the gravitational acceleration downward. Okay, so here the acceleration is given in terms of the gravitational acceleration, 0.20 times 9.8. Okay, so this is the acceleration. Okay, and it says that she's descending downward. Okay, so the acceleration is accelerating downward with this value. Okay, and then she stands on a scale that reads in kilogram. Okay, So she is inside an elevator. So let's say this is the elevator. Let's say there is a scale, and let's say here she is. Okay. So during this acceleration, what is her weight and what does the scale read? Okay. So here two question. I mean two question. Her weight and what does the scale read? Okay. Now her weight is m times the gravitational acceleration. Okay, so weight or the gravitational force is equal to m times the gravitational acceleration. So if her mass is 65 kilogram, then her weight will be this one, 637 Newton. Okay, so this is her weight. So we answer this question. Now, what does the scale read? Okay, so here something to remember is, so when in any question say that someone is standing on some bathroom scale or some scale, okay, scale reading is equivalent to normal force. So remember that scale reading, okay, scale reading, if someone is standing on a bathroom scale, it is equivalent to normal force. Okay, and here it is little bit different because the scale reads in kilogram. So that means even it is the normal force, in this case it will be the normal force divided by gravitational acceleration, that means 9.80. So in this problem it is this, the scale reading is this, but normally scale reading is basically just equal to the normal force. Okay, so here because it says explicitly the scale reads in kilogram, so we have to first calculate the normal force and then divide it by the 9.80, okay, to get back the number in kilogram. But normally in all other problem, in some homework problem, you will see similar problem, not exactly the same, okay, similar problem. But remember that if it is not explicitly mentioned that the scale reads in kilogram, that means the scale reads basically the normal force. Okay, all right. So normal force, sometimes called the apparent weight. Okay, why it calls apparent weight? It's called apparent weight because if the object is, if I mean if the lady is, this lady is on the scale, and if the elevator is not moving, it's basically the scale reading is basically basically her true weight. Okay, so true weight means her weight. And when you will see that when the accelerator is moving upward, accelerating, or I mean elevator is moving, I mean sorry, when the elevator is accelerating upward or downward, you will see that the reading changes, the normal force changes. Okay, so depending on the acceleration of the elevator, you will see that the reading of the normal force or the reading of the of this scale changes. Because it changes with the acceleration, we call it apparent weight. Okay, when the elevator is at rest, okay, it basically reads the true weight. When it is not at rest, okay, we see some different value. Okay, but the bottom line here to remember is scale reading is basically the normal force, is equivalent to the normal force. Although here to get the scale reading, we have to divide it by 9.80. Okay, and we call them we call this normal weight as normal force as apparent weight, because this is the thing we see. Okay, how I know that my weight is, I mean this lady's weight is 637 when she stands on this scale. When the elevator is not moving, we can read this from the scale. Okay, so we basically see the true weight from the normal force, okay, when the elevator is not moving. Okay, so because we see this normal force as our weight, we call it apparent weight. Okay, all right. Now the next part of the first question is, what does the scale read? So we have to do that. We have to calculate this. So we have to basically calculate the normal force, and then we have to divide it by we have to divide it by 9.8. Okay, so if I draw the free body diagram for this lady, so the lady is, so let me call it our coordinate system y, x. So the lady is here, the lady's gravitational force is this, or her true weight, and then this is the normal force, and the accelerator, the elevator is accelerating downward. Okay, so because it is moving downward, the direction of A should be downward. Okay, now let's write down the equation. Fy equal to may. So what is Fy? What is the left hand side? Left hand side is plus n minus mg, and then here on the right hand side we have minus ma. So this minus sign we have to use because the acceleration is downward. Okay, now from this we have to calculate what is the normal force. So the normal force is mg plus ma. So m is 65, g is 9.80, m is 65, a is 0.20 times 9.80. So this is a. Okay, so if you plug all these values correctly, you should get 510 Newton. Okay, so the scale reading will be 510 Newton divided by 9.8 meter per second square, and that is equal to 52 kilogram. Okay, so the scale reading here will be 52 kilogram. So you see that her true mass is 65 kilogram, but the scale sees 52 kilogram when the elevator is accelerating downward with some acceleration. Okay, so that's why we call it apparent. So here we basically should call it apparent mass, okay, or apparent weight. If we use this value, I mean, if we use this value, then we should call it apparent weight. Okay. All right. Now the next question is, what does the scale read when the elevator accelerates at the same acceleration but upward? Okay, so it's basically very similar. So only one thing we have to do is we have to change the direction of A. Okay, so the direction of A is now upward. Okay, so what we have to change is, okay, so it's basically the same thing. We have to change this to plus, okay, because now acceleration is upward. Okay, oh sorry, sorry, in the last problem, yeah, I did some mistake. So in the last problem it was this, okay, because it was this. So yeah, okay, in the last problem we should have a negative sign. In this problem and the second problem it should be positive. Okay, so yeah, all right, so in this problem this is positive. Okay, so this is positive, this is positive. Okay, Now it is not equal to this, it will be equal to 764 kilogram, sorry, 764 Newton. Okay, so in this problem the scale reading will be 764 Newton divided by 9.8 meter per second square, and that will be equal to 78 kg. Okay, so when the elevator is moving, accelerating upward with some acceleration, you see that it is higher than the regular mass. Okay, so her mass is 65 kilogram. When she is moving downward, accelerating downward, her mass is less than the regular mass. When the elevator is moving accelerating upward, her mass is higher than the regular mass. Okay, all right, so what next? What does the scale read when an elevator descends at constant speed? Okay, so you have to remember that constant speed means acceleration equal to 0, right? A equal to 0, right? That means delta V. Constant speed means initial and final velocity is equal to 0. There is no change in the velocity. Okay, so that means delta V equal to 0. Delta V equal to 0 means acceleration is equal to 0. So then if the elevator is moving at a constant speed, then you know that the right hand side is equal to 0. So n minus mg equal to 0. So n equal to mg, so it will be 637 Newton, and then divided by 637 Newton divided by 9.8 meter per second square will be, so this is number C, will be just 65 kilogram. Okay, so when the if the elevator descend at a constant speed, the scale basically reaches the same 65 kilogram. Okay, all right. Now the last one is, what does the scale read if the elevator cord breaks and if it is in free fall? Okay, so when the elevator breaks, the elevator cord breaks, the elevator, the woman and the elevator both are moving downward, okay, with acceleration equal to the gravitational acceleration. So for the number D, the free fall acceleration means the acceleration is equal to 9.8. Okay, so for number D, the acceleration now is gravitational acceleration. So again, let's write down the Newton's second law. Again, n minus mg, and then minus may is now the gravitational acceleration, right? Because acceleration is equal to the gravitational acceleration in free fall, and negative sign because the gravitational acceleration is downward. Okay, now you see that n equal to mg minus mg, and that is equal to 0. So the scale reading this time is equal to 0. Okay, so what it means? It means although the lady has her true weight equal to 637 Newton, when the elevator cord breaks, when the elevator is in free fall, the lady feel apparently weightless. Okay, apparently weightless because the scale reading is equal to 0. Okay, all right. Let's move on. All right, so let's try this one. So this is a vector problem. You know that force is a vector quantity. Okay, now we have two forces acting in two different directions. Okay, so one person is applying a force 40 Newton in this direction, another person is applying 30 Newton is in this direction. Okay, so we have to calculate the net force. Okay, now it's basically very similar to the vector addition problem you learned in chapter 3. So let's apply the same technique and solve this problem. Okay, so when we have two forces, okay, if they are not along the x-axis or along the y-axis, we have to break it, okay, into its component and then follow the rule that we already learned in last chapter. Okay, so let's see what we learned in last chapter. So let's break FA into its component first. Okay, so this is one component and this is x component. Okay, so this is FA y because this is parallel to the y-axis, and this is FAX. Okay, now let's first write down FAX. So FAX is FA cosine 45 degree. Now FA is 40 Newton cosine 45 degree, that is equal to 28.3 Newton. Similarly, FAY will be FA sine 45 degree. So it will be 40 Newton sine 45 degree. And again, if you plug this value in your calculator, you should get the same value. Okay, so FAX and FAY. Now, how about the FB? Okay, so for FB, so this is one component and this is another component. Okay, so this is FBY and this is FBX. Okay, so FBX equal to FB cosine 37 degree. Okay, so FB is 30 Newton and then cosine 37 degree, and that will be equal to 24 Newton. Similarly, FBY is FB sine 37 degree. Okay, so when you solve this kind of problem, remember that opposite to the angle is related to the sine theta and adjacent to the angle is cosine theta. Okay, so that we use here. Now here for FBY, you see that this is downward. Okay, this is downward. Okay, so because this is downward, we have to use a negative sign. So you have to understand also this. Okay, if you don't use a negative sign, you will get a wrong answer. So it will be something like this. Okay, and this is minus 18.1 Newton. Okay, so this is the difficult part, finding the components. So once you have the components, then the rest of the stuff is very simple. Okay, so the next thing what you have to do is fx. You have to find fx. Fx means you have to add this one with this one. Okay, so fax plus fbx. So what it means, this plus 24 Newton, and that is equal to 52.3 Newton. The same thing, Fy equal to Fay plus Fby, and again it is 28.3 Newton minus 18.1 Newton, and that is equal to 10.2 Newton. All right. So the next is F. So next is, what is F? So the magnitude of F is Fx square plus Fy square. Okay. So 52.3 square plus 10.2 square and then square root. So that gives me the force equal to 53.3 Newton. So the net force is equal to this. Okay. All right. Then how about the angle theta? So when we have this kind of problem, we basically interested both on the magnitude and the angle. Okay, and the direction. The direction means basically the angle. So the magnitude is this, and the direction is theta equal to tan inverse Fy Fx. Okay, so here Fy is 10.2 Newton and Fx is 52.3 Newton, and that is equal to tan inverse 0.195. So tan inverse 0.195 is equal to 11 degree. So the angle here will be 11 degree. Okay. So let's solve one more problem today, and then the rest of the things in the next class. Okay, so the last problem for today's class is this one. Okay, so we have a 15 kilogram sled is pulled by a force of 60 Newton at an angle 30 degree, as shown in the figure. So calculate the acceleration of the sled and the magnitude of the normal force. Okay, so when we have this kind of problem, it's better to first draw the free body diagram. Okay, so let's try to draw the free body diagram first and then solve the problem. Okay, all right, so here is the sled. Okay, so the gravity, okay, mg, you should have normal force. Okay, now this p we have to break, so let's break it. Okay, so this is py and this is px. So py will be p. So if this is theta, so it will be p sine theta, because this is opposite of theta, and this will be p cosine theta, because this is adjacent of theta. Okay, and if there is acceleration, the acceleration will be in this direction. Okay, there will be no acceleration along the y direction. So this is basically the free body diagram. Okay, now let's first try to calculate the acceleration. Okay, so to calculate the acceleration, we have to use this equation, Fx equal to max. Okay, because the acceleration is along the x direction. Okay, now what forces acting on the x direction? We have only px. All right, there is no other forces along the x direction. So px equal to ma, and this is positive, this is positive. Okay, or px is equal to p cosine theta equal to ma. So a will be p cosine theta divided by m. P is 60 Newton, cosine theta is cosine 30 degree, and then m is 15 kilogram. So if you do this math in your calculator, you should get 3.46 meter per second square. Okay, all right. Now how about number B, the normal force? Now to calculate the normal force, we have to use this equation, Fy equal to may. Okay, because the normal force is along the y direction, but this is 0, right? The acceleration is 0, so right hand side is equal to 0. On the left hand side we have several forces, n positive, and then plus py, and then minus mg, that is equal to 0. So n will be mg minus py, or mg minus p sine theta. So m is 15, gravitational acceleration is 9.8, minus p is 60 Newton, and sine 30 degree. Okay, so if you plug all these values in your calculator correctly, you should get the normal force is equal to 117 Newton. Okay, so I'm going to stop here. We may need one or more lecture, the problem solving lecture, so for this chapter. Okay, maybe one, yeah, maybe one more lecture. All right, so I'm going to stop it here. I will be talking more about this chapter problem in next lecture.